In this example, we want to write out the partial fractions decomposition to the following rational function on the left-hand side. For this example in particular, we really just want to focus on setting up what the decomposition looks like, and we're not going to go ahead and solve for the coefficients. This problem is really about how do we set up the decomposition. So let's take a look at this function. So this rational function we're given, it looks pretty complicated. It also sort of looks like that denominator is already factored for us. However, we want to go ahead and make sure that this denominator is fully factored before we write out any terms in this decomposition. Now, if we look at this denominator real close, well, this x minus 2, that is a distinct factor, so this one's all fine for us. However, this x squared minus 4, we can actually go ahead and factor this. Okay, if we were to actually plot what this function looks like, this function looks like the following parabola. And what I want you to notice is it has two roots. And the reason I'm showing this is because this is a function that has roots, we're going to be able to, or this is a polynomial that has roots, we're going to be able to factor it further than what's already written as. So without further ado, I'm just going to go ahead and factor this. And we could, of course, hit this with quadratic formula if we wanted to look for those factors, but we could also just see that, well, this is one of those cases where we don't have any x to the first type terms in there, so we're going to get an x plus x minus the same number, and this thing's actually going to factor for us pretty nicely to x minus 2 times x plus 2. All right, so now moving on to this last term, this x squared plus 4, we got to ask ourselves, is there any way we could continue factoring this? And well, if we do the same thing like we did for the x squared minus 4 case, if we go ahead and try to plot this function looks slightly different now. So again, this is now x squared plus 4. What we notice is this function doesn't go ahead and doesn't touch the x-axis anywhere. So it doesn't have any real roots. Its only roots, if we were to use the quadratic formula, would be complex. So because of this, this x squared plus 4 term is actually irreducible right now. We can't factor it any further. So I'm just going to make a little note of that. This term, this one is irreducible. So let's see what we have now. We have something that looks pretty similar. However, I want to draw your attention to one thing. Once we factor that x squared minus 4 term, we have this factor of x squared or x minus 2. We also have another factor of x minus 2. So we're going to get repeated factors once we had factored that overall denominator further. Okay. So I'm just going to rewrite what we have here. This is 3x minus 11. That just is what it is in the numerator for right now. In the denominator, we have a single factor of x minus 2, or x plus 2, excuse me. We have two factors of x minus 2, so I'll say x minus 2 squared, and we have that last irreducible factor of x squared plus 4. So now we can start writing out what this decomposition looks like. The denominator is fully factored. We see what repeated factors we have, what distinct factors, what irreducible factors, so we can start writing out this decomposition. I'll also make the note that in this particular problem, this is really about how do we write out decomposition. So this numerator in this case, if you notice, the highest power of x is a x to the first, and we have higher powers of x in the denominator. So we don't have to do any polynomial division right from the get-go on this problem. All right, so if we write out these decompositions, first, let's take this distinct factor. So we can just write this as some unknown a over that distinct factor, x plus 2. Now, let's focus in on this repeated factor. And remember, when we have repeated factors like this, we'll need terms up to the power of this repeated factor. So in this case, we have x minus 2 is repeated twice. So in the decomposition on the right-hand side, we're going to have two terms that describe this. And those two terms, the way we write them is we have an unknown, so in this case, b, over x minus 2 to the first power plus another unknown, say c, all over x minus 2, but this time raised to the second power. And now for this last term, this is our so-called irreducible term. And if we write this term out, we will have in the denominator an x squared plus 4. And then while in the numerator will change from just one single unknown constant to we'll actually have the general equation of a line. So in this case, we'll have a unknown constant, say d, times the variable x plus another unknown constant, say e. So this is what our partial fractions decomposition looks like in this case. And we have 5 unknown constants, namely a, b, c, d, and e, that we would try to solve for by setting up systems of equations and looking for those 5 unknowns. But in this example, this is what the decomposition looks like. And remember, the way we're able to see this was we made sure that denominator was fully factored to see what distinct factors we had, what repeated, as well as what irreducible factors we also had.